All right, well, welcome back to Engineering 270. This is lecture 6B. So I apologize for the audio quality on that last segment. That was an amped up microphone or something, so hopefully you could figure out most of what I was saying, and hopefully this one is better. We're going to talk about something called an interrupt, or interrupts in general. And this will use the idea of call and return and a stack pointer and these other things that we just talked about, but it's really kind of a subject in itself. So what's the motivation for an interrupt? Well, for example, when you get a text message on your phone, how do you know that you got a text message? Is it because you're constantly staring at the screen? You keep unlocking your phone to see if you have a text message? No, it's because probably you have a vibrator or a ring set up, and when you get a text message, it does something to get your attention. The phone makes a noise that gets your attention. It interrupts you. So if you're sitting there writing code and you hear this sound from your phone, you temporarily stop writing your code, you turn to your phone, you unlock it maybe, and you see who sent you a message. And maybe you respond to it, and maybe it takes you down a long path where you do a whole bunch of things. But at some point, when you're done dealing with that interrupt, you go back to where you were. You keep typing in your code from where you left off, and so on. And if another text message comes in, it makes a noise, it interrupts you where you are, and you deal with that. And then when you're done dealing with it, you come back and you continue where you were. That's the basic idea of an interrupt. We use these all the time in our lives. And they're really useful to have inside a computer. For example, you may want a program that does some sort of computation, or it updates a display or something like that. But at any time that a button is pressed, it's going to do something different. And you don't want to have to constantly keep checking the port that that button's connected to, saying, is the button pressed, is the button pressed? You'd like to be able to do your own thing, but know that when a button is pressed in a certain way, your code will respond immediately. Okay, so that's the goal of having an interrupt. And we're going to deal with one particular type of interrupt for now, but there's a lot of other types, and some of these we'll talk about later. But this is a hardware interrupt triggered by raising the voltage on pin 8. So pin 8 has this function of INT0, interrupt 0. Pin 9 is INT1, pin 17 is INT2. We can hook a switch up to pin 8, for example, and normally put in 0 volts, but arrange things in software so that if we put 5 volts into here, it will generate an interrupt. And whatever the computer is doing at that moment, it will go off and handle some other piece of code, run some other piece of code to handle that interrupt, and then go back to where it was, just like we do when our phone buzzes and we check for a text message, we send a reply back, and then we go back to where we were. Alright, so what happens when we get an interrupt? The system basically does something like a call, and it calls location 8 in instruction memory. Why does it do that? Because that's what the designers told it to do. It's not something we can modify, it's not something that other systems will necessarily do, but this is what the PIC processor does, this particular PIC processor. When you get an interrupt, it jumps to location 8, but it does it with something like a call, which means the address of the next instruction that you're going to execute is saved on the stack, which means that later on you can do something like a return and get back to where you were. Okay, so how do we make interrupts work? Because normally if I raise pin 8, this does not happen. So how do we make interrupts work? Well, we have to work with a series of registers. One is called RCON, and the other is called INTCON. And let's take a look at those registers. So RCON is a special function register. The first thing you want to do is set bit 7 to a 1. Okay, so let me use some notation. That's an angle bracket. This says RCON bit 7 should be set to a 1. But you notice we have a name for bit 7, it's IPEN. So don't write this. Think of it like this, RCON bit number IPEN should be set to a 1. And in our code, we can refer to IPEN, and it'll translate to a 7 because it's bit 7 in this register. So that's the first thing we do, and this basically says that we're going to want modern interrupts. We're going to want interrupts that can come in on 2 different levels. Okay, the other register we need to deal with for now is INTCON. And intcon, we basically want to set 2 bits. We want to set global interrupt enable high to a 1, and we want global interrupt enable low to be a 1. This is bit 7 and this is bit 6. It's got multiple names, but let's use global interrupt high and global interrupt enable low. So we set those 2 bits. That allows interrupts to take place. Okay, the last thing we want to do is we want to set this interrupt 0 interrupt enable, and this is also an intcon. So we set intcon int 0 interrupt enable to a 1, and that allows interrupts to come from this int 0 pin, which is pin 8. Right, int 0 pin 8. So we want rcon ipen to be a 1, intcon gieh, intcon giel to be 1, and intcon int 0 ie to be a 1. And these are just coming from chapter 9 in the data sheet, and there's a separate handout I'll put on Canvas that has all of these registers available to it. Okay, once we've done this, if at some point pin 8 changes from 0 volts to 5 volts, we're going to find ourselves suddenly at location 8 in our program memory. And so at that location, we should write code that does whatever we wanted to do in response to that button. Okay, when we're in our interrupt code, we'd like to know, is this really pin 8 that caused the interrupt? Because lots of different things can cause interrupts, and they all cause a call to location 8. So there's this bit int 0if, that's the interrupt flag, and that will be set to 1 down here if the interrupt was caused by int 0. So we want to do the following check. Is intcon bit int 0 interrupt flag equal to 1? And if it is, we know that we got an interrupt request because that int 0 pin 8, raised from a 0 to a 5 volt level. So we can do whatever we want. We can, update some counter or change something. We could do a small number of things. We could do a huge number of things. When we're finished, we would like to return back to where we were. But you got to do a few things before you return. One, you've got to clear this interrupt flag. You got to take intcon int 0if and set it to a 0. If you don't do that, then as soon as you return, you're going to get an interrupt right away, because it's really this bit being equal to a 1 that causes the interrupt. So you got to set that interrupt bit back to a 0. And the other thing is, instead of doing return, we do a retfie. R-E-T-F-I-E. What does retfie do? Well, it does a return from the interrupt, but it also re-enables interrupts. Because once we're getting an interrupt, we can't get interrupted again. Okay, this is better than a cell phone. While you're reading your text message, you're not allowed to get another ring from your phone saying, hey, you just got another text message. Okay, so it forces you to do one thing at a time. You get an interrupt because pin 8 raised, and you start doing things inside this interrupt routine. If another interrupt occurs, you won't get interrupted until you finish what you're doing right now. So basically, interrupts are disabled while you're inside an interrupt routine. Retfie re-enables interrupts and then does a return, but it does it as a single instruction. If you try to do it manually, it's possible you can get interrupted before you execute the return, and then you've got a problem. All right, so that's the basic setup, and getting comfortable with using these is just something that takes a lot of practice and experience, but the basic mechanism is straightforward, right? So we enable priority levels on interrupts. We always do that. If we want high priority interrupts, we set this to a 1. If we want low priority, we set this to a 1. And then we enable the particular interrupt that we want, int 0 in this case. When the interrupt occurs, we jump to location 8. In location 8, we can check to see if this IF bit, the interrupt flag, is set. And if it is, we know that int 0 is what caused the interrupt. We do our interrupt processing. And then when we're done, we set the interrupt flag to 0 to clear the interrupt, and we do a retfie. All right. possibly that sounds pretty straightforward, and in some ways it is, but the ways in which we can get tangled up with interrupts are enormous. There's a lot of things that can go wrong here. And because interrupts are triggered by usually outside events, there's no way to predict where we're going to be in our code when an interrupt occurs. Which means you might write code that works great 5 times in a row, and the next time you try it, it totally breaks, because you happen to be in a section of your code where the interrupt exposed a bug in the way you're handling interrupts. Okay, so let's just look at one thing that can go wrong, and this is the idea of something called a side effect. So what is a side effect? It's a change that you didn't intend to have happen as a result of processing the interrupt. So we want to avoid undesirable or unintended side effects. Okay, some side effects are good. For example, when you push this button, I want to increment a counter. So the fact that the counter incremented, that's a desirable side effect. But the fact that I destroyed the contents of the status register just before I was about to do a conditional branch, that's an unintended side effect. So here's the idea. Let's say we say decrement file count, and then branch if not 0 to do more. And somewhere up here is our label more. And suppose I have some interrupt code, so down here at location 8, do stuff. And I don't know. Let's move a 0 into W. Move W into some file register called stat, and then let's return from the interrupt. Alright, so I'm sitting up here, I'm doing my loop, I'm decrementing a counter, and if it's not 0, I'm going to go back up here and do some other stuff. I'm going to decrement my counter, if it's not 0, I'm going to go back up here and do other stuff, and so on. Okay, and suppose that count is currently equal to 17. Okay, and I decrement my counter, so count is now equal to 16. And I'm about to execute this branch if not 0. And remember, branch if not 0 will check the status register, and when I decremented count was equal to 16, so the 0 bit is false. So when I say branch if not 0, it should branch back up. But suppose right here, I suddenly get an interrupt. I jump down to location 8, I do some stuff. At the end of my stuff, I put a 0 into W, I put that into a file register called stat, and I say return from interrupt. What is the Z flag right now? See, when I did this move literal W0, that set my Z bit to be true. And when I move that into stat, the Z bit is true and I return. So when I come back from my interrupt, Z is true. And when I say branch if not 0, it's going to say, oh, Z is 0. It's not going to branch, and it's going to go on to the next instruction. So I've got this code that I thought was going to loop 17 times. It looped once and then it exited. Why? Because I got interrupted right here, and my interrupt had an undesirable side effect, which was it changed the value of Z. It could also be I was doing something with the W register in here. For example, maybe before I got into this, I moved the literal 12 into W. But in my interrupt code, I loaded a 0 into W. So when I come back, W is no longer 12. W is equal to 0. That's another undesirable side effect. Alright, so what we want to make sure is that whatever we do in our interrupt routine, when we return, it looks as if nothing happened except for the things that we want to have changed. So we need to save things that we're going to use and modify. For example, if we're going to change the W register, we should save the W register before we modify it, and then restore it at the end. Same thing with the status register. Well, it's a little hard to manipulate these things without actually causing changes to occur. So there's a helpful mechanism in the PIC processor. There's something called shadow registers. And it's a single set of storage locations that will save the W register and the status register. And when we do our retfee, if we say retfee 1, it will restore those registers from the shadow registers. So if we said ret fee 1, then when we return, Z would be set back to the value of false, and W would be set back to its value of 12. So usually you're going to want to do a ret fee 1 when you return from an interrupt. The trick is there's only one set of shadow registers. So if you were to get interrupted inside an interrupt routine, you need to handle saving those registers yourself. That's a detail we'll talk about more another time. So two more things to note. One, there's two priorities of interrupts. There's a high priority, which is what we've been talking about, but there's also a low priority interrupt. A low priority interrupt, when it occurs, vectors to location 18 hex. High priority jumps to location 8 hex. So low priority interrupt takes you to a different location. And if you're in the middle of a low priority routine, you can get interrupted by a high priority interrupt. But if you're in a high priority handling routine, you won't get interrupted by a low or a high priority. So a higher priority will interrupt you while you're processing a lower priority. We only have 2 priority levels on the PIC. Some systems have 32 different priority levels. So this is a pretty coarse priority system, but it lets you do something like some low priority event, like someone pressed a button, you can start handling that. But then if some high priority event happens, like the power starts to fail, you can say, I don't care that you're doing an interrupt right now, you got to take care of my task right away. And that's the high priority part. So they just vector to different locations. The other general comment is you need to be really, really good about looking at the registers that you're going to use for interrupts. For example, when we want to deal with int 0, right, we had to use incons interrupt enable bit, we had to use incons interrupt flag bit, and so on. That's only for interrupt 0 though. If you want to deal with interrupt 1, you have to look at the incon 3 register. And incon 3, here's the interrupt enable and interrupt flag for interrupt 1 and interrupt 2. Right? Remember, interrupt pin is pin 9 and interrupt 2 is pin 17. So those enable and interrupt flag bits are in a totally different register. And if you try to set those in incon 0, it'll let you do it, but it'll do something totally different. Ints 1 and 2 we can also set the priority of. For example, interrupt 1, we can set it to be high priority or low priority by setting this int 1 IP bit in incon 3. Int 0 is always high priority. So we can modify these routines in a number of ways. We can also control whether the interrupt occurs when the pin raises from 0 to 1, a rising edge, or from 1 to 0, a falling edge. And that's controlling the incon 2 register. So if we set bit 7 int edge 0 to, bit 6 to be a 0, it will interrupt on the falling edge. So that when the input goes from 5 volts to 0 volts, that's what triggers the interrupt. So this system is highly customizable. And it's really a question of getting comfortable with all the different registers and playing around with it. And we can do all of this in the simulator also, so that's going to be a useful tool for digging deeper into this. All right, that does it for Lecture 6B.